Let's now see the fixes. And we want to split the event ML out according to the two cases that we spoke about. And similarly, we want to also split IO out based on the exercise that you're supposed to do. I'm going to give you some guidance as well. Okay, let's talk about ML out. ML out is going to split into two events. Each one of them is going to have the guard for case number 1 and the guard for case number 2. Remember, for case number 1, after the car going out of the island onto the bridge, if they haven't really reached the maximum, in that case the green lights can remain. Otherwise, if after the car actually goes out of the island, if we have already reached the maximum, in that case we should really turn the traffic light to be red. Symmetrically or analogously, after you do the exercise for IO out and also invariant 2-4, both to specify it and also to prove it, you will see some unprovable sequence that will give you a similar hints. Let me just give you some guidance over here. The hints should be about after the car. Remember, IO out is really about some car going out of the island. If after the car going out of the island is such that the remaining car in the island is not equal to 0, in that case, the traffic light can remain green because there might be more cars coming out of the island. Otherwise, if after the current car goes out of the island, the count just becomes 0. In that case, there's no more car that can really come out of the island, in which case we should really turn the traffic light to be red. Right? So these are the two hints you're supposed to get by doing the exercise. I'm going to rely on you to do the exercise and reach out to me if you got any trouble. Let's now see the final revision result. ML out is going to be split into ML out 1 and also 2. IO out is going to be split into 1 and also 2. Let's see more closely about the guards, which will correspond to the two cases that we analyzed. For ML out 1, the guard is about adding 1 to A. It's not going to reach the maximum, in which case the green lights can remain. We don't have to turn the red. On the other hand, in the case where A plus B plus 1 reaches the maximum, in that case we have to turn the traffic light to be red. Right? That's exactly what we discussed. Symmetrically, in the case of IO out, which is going to decrease the counter in B over here, if after the decrements of B because of the current IO out, if it hasn't really reached the minimum value 0, in that case we're going to let the green lights remain to be green, of course. And notice that I write this slightly differently over here. That's kind of according to the textbook, but you know pretty well B not equal to 1 is really equivalent to B minus 1 not equal to 0, right? They are really equivalent. I'm just showing you two versions. What about the other case? For IRL2, we are saying that after B minus 1, if that really reaches 0, right? You can see this one here can really be rewritten as B minus 1 equals 0. If that's the case, we have to turn the light to be red. So these are the two split events, but let's try to visualize them once more, and then we can actually talk about some exercises for you to do to really make sure you got as much understanding as possible. Right? It's really important to see right from the beginning why we are doing this, how we come up with the two cases, and also how we adopt the two cases into the guards and also the action over here. It's really important for you to see that. Let's talk about this one over here. How exactly do we expect the two events to really occur? For ML out 1, that means when we got ML out 1 over here, in that case, what we're expecting to see is the MLTL is currently green. And also, A plus B, let me rewrite it in a way that we are maybe more intuitive. You can think about A plus 1 and then plus B not equal to D. That means we haven't reached the maximum. In that case, all we're going to do is we can safely increment A because we know that A plus 1 plus B wouldn't reach the maximum. So that's okay. We can keep doing this until the very last time of ML where we're going to reach the maximum D. What's going to happen is, so ML can really keep happening, right? You can ML 1, beg your pardon, it should be ML 1 over here. This can happen for as many times as necessary until we get to the last one, which will be ML out. right? ML out 2. What's going to happen is, remember here, one of the enabling condition is A plus 1 and then plus B reaches exactly the maximum. In that case, what we're going to do is we're still going to allow the last car to really go into the breach. And then at the same time, we're going to turn the traffic light over here. Rather than green, is going to be red. That's what's going to happen. So you can imagine what's going to happen is we're going to have multiple occurrences of MLR1. And as soon as we get to the last one, which is going to make the total count reach the maximum D, in that case, we're going to turn the traffic lights to be red. So no more cars can really come out of the main lane onto the breach. That's really what's happening over here. Symmetrically, we can also expect multiple occurrences of IR out 1 for as many as the current value of B might actually allowed. And then it's going to be finished by a final occurrence of IR out 2 before this traffic light is turned red. But let's see exactly what's happening over here. It's really worth reiterating the points again, so make sure you really understand our design rationale. So what we can expect to see is we start with IL out 1. So IL out 1, meaning that there's one car waiting over here to really go onto the breach. And of course, ILTL should be green. So this one should be green lights over here. And the condition is B minus 1 not equal to 0, meaning that if we allow this particular car to really go out of the island, in that case, we can decrement the counter of B by 1. And it hasn't really reached 0, meaning that the green light over here can remain. And this can really happen for as many times as the current value of B might allow. For example, if we got 10 over here, we can expect maybe 9 occurrences of IRR1 before the very last IRR2. Okay, let's now talk about it. So for this one, let's talk about IRR2. So this can be as many as you like for IRR1. And the final one is going to be IRR2. IRR2. And the condition will be B minus 1 is equal to 0, meaning that if we allow this final car to really go out of the island, decrementing it is going to reach B being 0. In that case, we should really allow, of course, we can still allow this car to really go out of the island. That's fine. However, since after that we got 0 car in the island, so we should really at the same time turn this light over here to be red. That's what we should do. So you can see the way the MLR1 works is similar to IRR1, and the way MLR2 works is also similar to IRR2. You should really see the correspondence over here. Okay, let's now go back to the slides. I do have some exercises waiting for you to really make sure you can strengthen your understanding about what's really going on. Right? Let's talk about the exercises. Right? That's a summary about the splits that we just went over. Exercise number 1. You want to really specify and prove these two invariant preservation over here, ML out and also IL out, and also invariant 2-3 and invariant 2-4. And exercise number 2. Given the latest model M2, how many sequence do we need to prove for invariant preservation? Think about if you want to regenerate all the sequence, how many do you need to generate? Okay, it will be very important. How many events do we have now? I can tell you that we used to get 6, right? If you remember the magic number, we used to get 6. However, it should now be increased into 8 because we got, for ML out, it's really split into ML 1 and 2. So we got plus 1. And also for ML IL out, it also split into IL 1 and IL 2. So we got another plus 1. So that's why we got 8 events in total right now. Right? So you really want to see how the math works. So this 8 over here is because ML out splits into ML 1 and 2. And also IL out split goes from IL out, just one single event, into 1 and 2. So that's why another plus 1. And given that we got 8 events, how many invariants do we have? The number of invariant will be 5, right? Remember we added 1 invariant 5 about that both traffic lights cannot be green at the same time. So in total, number of sequence for invariant preservation should be 8 multiplied by 5. That should be 40. Right? So that should be the number of sequence that should be proved in total. All right? That's very important to always apply the formula and know the result. Finally, each split event, for example, MIR1, refines its abstract counterpart. Right? That's also something I want to talk about over here. Right? It's also important to see what's happening over here. Let's talk about refinement relationship. We talk about M1, the abstract model. Let me use green. M1, the abstract model, we got, for example, MI out. And also we got IL out. After the split, what we are having now is, in the current refinement model, the more concrete one, somehow is split into ML out 1 and also ML out 2. Right, I'm going to tell you exactly what I intend to assign to you as exercises. And also this will be IL out 1. Also split into the second case, IL out 2. What you really want to prove is as follows. You want to prove that this one here refines this abstract counterpart, and this one also refines that. And similarly, this IL1 refines this. This IL2 also refines that. And what should we prove about our refinements? Here is my biggest hint for you. You don't really want to think about MIR1, MIR2, and these two as the new events. They are not really, because I said both of them have the same abstract counterpart. And both of them over here also have the same abstract counterpart. So they are not really new events. In this case, for example, you don't need to prove about convergence. You don't need to. Convergence proof is only for new events. Let me write it down. That'll be a very big hint for you to think about how to prove refinements when we actually got the splits of these two events. So all these over here, they will still be considered as old and concrete events. Not new events, because they indeed have their abstract counterpart. In that case, for example, a graph strengthening should be really proved. And you definitely can refer back to how we actually proved about the first refinements M1. In that case, you think about how we treated each concrete old events. In that case, they should be applied to these 4 events as well. All right, so that's something I'll leave to you as an exercise to really make sure you sketch about the roadmap about proving the refinements. Is really important for you to know how exactly to do that. You don't necessarily have to attempt all the proofs because the number might be quite large, but at least try some of them, and also to get the roadmap very clear. Let's now go back here. Right, so that's about the 3 exercises. I would suggest you actually carefully think about them, and before we move on to the next part. Unfortunately, our model is still subject to further improvement, and we're going to talk about them